Sup guys, welcome to today's show. So, I am writing my own operating system, but in order to properly do that, I need a printf function which works in a 16-bit environment. And that's because every PC boots up in 16-bit mode and I need to be able to debug it properly. So that's why. However, this project of today is completely separate. So let's begin. Alright, so let's go into this OS kernel project. You can find it in the repo in the description. Create a file, I'm going to call it pf.asm. Okay, so the point is I want this to work with both 16-bit real mode, so we will print to the screen using BIOS interrupts, and 16-bit protected mode, in which case we're going to write to IO port E9, which will send it to the debug console inside of my virtual machine. So this time I'm going to use a instruction which is not used very often nowadays, because I wanted access to this Felix Asm. He has a lot of good assembly stuff. So here is the instruction. It's called enter, and it creates a stack frame. So I'm going to use this, let's see here, yeah, this one. So we specify enter, and then we say how much stack space we need for local variables. And this 0 at the end is the number of levels in the lexical scope, but we're not going to use that, so we will just put a 0 here. Otherwise we have a possibility to put another thing there. And I want to save as much as possible to the stack. Alright, so a capital first letter on the name of the functions that I'm going to export. So let's do that. Global put char real mode. So let's say that we take a int 8 as input, and we generate some return code. We don't need to do that actually. Let's just do this. And I want to preserve all registers except EX, because EX is going to be used as an output code, not for this function but for others. So we can't save EX, but the rest of the registers I want to save. So even though it's not very effective CPU-wise, not very optimized, I'm going to do it anyway. Yeah. Okay. So we need to get this thing out of the stack. So let's let's move into AX. The first argument is going to be BP plus 6. And then we're going to send it to the BIOS for printing. So let's see here. If we search for Stanislav BIOS 10H. So let's see, write character. We want to write it in teletype mode. Let's see here. There. Write text in teletype mode. Okay. So this is what we need. So let's paste this in here as a comment. Alright, so the character needs to be in AL, which it is after this. So we need to put 0E into AH. And we need to clear EBX, which means we need to push it as well. BX, by the way. We need to pop it before we leave. Okay, so we clear out EBX and then we issue the video interrupt. And now it should have been printed, and then we pop BX, leave and ret. This should probably be it. And what I'm going to do is I'm going to create a temporary thing, which I'm going to call let's call it temp main. And here I'm going to test the function. So let's say we do push, let's move something. Let's say we clear out AX, we move into AH, A, push AX, and we call put real mode, and then we need to remove that thing from the stack, so we can add SP04 2, I mean, they are 16 bits values. And then just do some endless loop kind of thing. Something like this. Then I'm going to export this. I'm going to remove this temp main when we are done, but this makes stuff a little bit easier because now I don't have to worry about the other files. Let's do this. So we add PFO here. Close down the loader and we open up the X kernel. Like so. Okay, but it's not printing, is it? Okay guys, I found the error. So now it works. It prints the A. It was a stupid error, as it often is. I had put bits 32 here instead of bit 16, so that's why. And also this should be BP plus 4 for the first argument, not 6. Okay, so now we have something to work with. We can close down those other files and clean this up a little bit. Alright, so let's create the other putchar function, which will be pretty similar. We're gonna have, by the way, this is putchar real mode, putchar protected mode. By the way, this version works for both real mode, so maybe we should let's do it like this. So this is of type int8 to void, same as the other, and it will be almost identical. So we set up the stack frame and take care of the arguments. This time we don't need to move anything into AH though. The only thing we're going to do is we're going to output a byte to port E9, and that byte is AL. That's all. Which means we don't need to push BX, because we're not overwriting that. We don't need to XOR, we don't need to do any interrupts. We just leave ret. So simple enough. One as well, putchar protected mode. Alright, so how do we code this printf thing? Instead of just outputting each byte directly to the screen, I want to do something which more resembles Asm printf, if you know what that is. In C it works like this. So we have an argument which is a buffer of some sort and a size, and then we do our format string and argument. So instead of just printing this to the screen, we will write it to this buffer instead. And then we can create a simple printf which just uses a temporary stack buffer and prints the thing. Yeah, so that's the idea. And because sometimes we need to do other things with a format string and arguments other than putting them to the screen. Okay, so how do we do this and what do we need to do? So I want to support a couple of things. I want to support %s, which is a string, and x, which in our case is going to be a 4-digit hex string. Possibly I'm going to support 2 digits, but that's not too necessary. And this is a number. So if I get these 3 to work, I'm glad. And if I only get this to work, that is the most important anyway. so maybe we should start at that end. We need to have a function which takes a number and it turns it into a string of hexadecimal digits. And then it needs to return not just the string, but also its size, I guess. Maybe we can do something similar. So something like hex to string, and let's say we provide a buffer and a size here as well. And then we take in a character. So something like, not a character by the way, a hex string. So something like this. And then it should write it like this to this. And then it will return the string. No, it does not need to return the string because it's writing it here. We can just return the number of characters written. Yeah, that's perfect, I think. Alright, so let's see if we can figure this out. Okay. So hex to string is of type, and we're going to take in a buffer. And we're going to take in a size. So let's see. An int 8 should suffice here. And we're going to return an int 8. So something like this. Okay, so this is hex to string. And same as before, we need to set up a frame here. So we enter, but this time we're gonna need some stack space. No, actually not, because we're writing to a buffer, so we don't need that. So we'll do the same as before with this. And let's put into di the first argument, and into, let's see, the size. I guess we can put it in cx. Something like this. but I want to make sure that this is no bigger than 255. So let's put this into AX instead, and then we 0 CX, and we move into CL, AL. So the result is basically the same, but now we don't have to worry about it being bigger than int 8. Let's make sure to push the registers that we use, DI and CX in this case. Alright, so how do we do this? Well, we need to take in the character too, don't we? And that is going to be an int 16. Character is a bad thing, let's call it num. Let's move into AX this number. BP plus 8. Okay, so now we have the arguments. Maybe we should also add some commenting here. So DI is equal to the buff. CX is the size AX is the num, CL to be precise. Okay, so we need to iterate through these characters. So we need to set up some kind of a loop. Which means it's better to use BX for this one, since we're going to have two loop conditions. So move into CX, and we're going to loop, since we're going to support 16-bit characters, which means we have A, B, C, D. So this is what we have. So first we're going to take care of this D, I guess, and then the C and the B and the A. So we're going to iterate 4 times. We set this to 4 and 3 and 2 and 1. So first we need to make sure that this this size here has not run down to 0. So we can do a compare of size and 0. We can jump if it's 0 to end. Otherwise we decrease the size. By the way, size is BL. And the other condition we take at the end. Alright, so we need to take out one of these characters. So we need to copy it to some scratch register. So what do we have left? We haven't used dx for anything. So let's copy our contents. dx from ax. Is that the best move? No, I don't think it is. It's better to do it here. So we move into first we need to zero out this thing. We need to push. So we're gonna use bx and cx. dx and di. Okay. So let's move into DL from AL. That means that we have CD now inside of DL. After we have done that, we can push all of these one step to the right, which means pushing them 4 bits. So this D will fall off, which means next time we will have these and so on. So we shift right AX with 4. And now we need to mask out this, because now we have DL equal to CD, and we need to grab at this D. So if we do an AND operation with this, that means that we will only have a D left. So we do an AND DL and 0F. So now DL contains that hex digit that we want to use. So now we want to transform that into a character. So let's see here. So if we have an F, for instance, so that's a 66. And we want to turn it into a 0xf, which is 15. So if we have the difference, if we have this minus this, so this is the difference. And if we remove this difference, we have this difference and we want to remove that from the original thing, which is this. And then we should end up with 15. Which we do. And does that work even for other numbers like this? So now it should be 14. Yeah, okay. But it does not work for instance, a 9. Because then we're here. So we need to first check if it's between 30 and 39. And in that case, we just want to remove 30. Okay, so we have two cases. We compare let's see here. We compare the contents of DL with 40, let's say. So if it's less than 40, jump if less. In that case, we wanna treat it as a decimal digit. Otherwise, a hex digit. So decimal. So if it's decimal, we just want to subtract from DL 0x30. No, I'm doing this wrong, aren't I? We are going the other direction. We have it in the lower numbers, so between 0 and 15, and we want to go to this. Okay, so what I should do is I should compare it to 9. And if it's greater than 9, we're gonna go to hex, otherwise to decimal, and we want to add 39 in this case. And if it's a hex value, then we want to add to DL the difference between here we have 66 and an F. Difference between 66 and 0 as F. That's what we want to add. Alright. So now we have inside of DL the ASCII character of the number, or the hex, the hex number. So now we want to write this to the buffer. And I think there's a good command for both writing and updating that stuff. Let's just double check. So if we search Felix .sv, so this goes the other direction. This loads into EX from a pointer. So what we want to have is something like store ESP. How do we usually do this? Let's search for SB. or sp. Store al at address di. And does it increase di afterwards? Ti, let's see, we have this di plus 1. Okay, so this is it. So we want to do a stas b. And it doesn't take any arguments because it takes its source from by the way, we use di here. Ah, that's right. So it uses destination from the di register, whatever this is pointing towards. Then it increases it by 1. And it stores that thing from al to this. So we need to copy into al. What do we have in al currently? We have the number there. So let's use something else for that. Si is a good fit. Now we just need to remember to update it at each and every place. This becomes SL. SI. Why does it look like this? Let's search for AX so we make sure we haven't forgotten anything. So this should be SI instead. And then let's also search for, maybe we can do this. Search for AL and AH. But it seems to search all over for that. Okay, so here we are in the right function, and we move into BL from AL. So this is before we start using the register. So this we should not change. And then there's no more. Okay. So before we do the stas, we copy it to the AL. So let's clean that Alt AX, move into AL from DL, and then we store that thing. So now we need to check for our CX condition. So we can probably just do loop, because I think the loop thing checks if CX is 0 and otherwise it jumps to that label, plus it decreases it by 1. Let's also double check that. Loop. Decrement count jump short if count is not 0. Okay. And the other counter we check here. So we compare BL to 0. And if it is 0, we abort. We should have some counter for the number of bytes we have written. Or is that necessary? I guess it's not. No, because we're always going to return 4. Since we're dealing with 16-bit numbers. So we can make this a void function. Okay, so SIDIDX. And then CX and BX. And we'll leave and return. Yeah, I think this is cool. Let's try it out. So instead of doing this right here, let's move into AX and we take some number 0 F49, let's say, and we push, then we call hex to string. By the way, we need more arguments. We need the buffer and the size also. So what buffer should we use? Let's just take something here for now, TMP. And here we will define So we have pushed the number, now we're going to take the size and then the buffer. Okay, so size can be a big value, it doesn't have to be exact, because this is the most that we can use. So let's try a really big thing first. Let's say 5255, which is something we probably will use quite a lot in this case. And then we need a buffer as well. So let's create one. Let's call it buff. And let's make it 8 as well. Then we call hex to string. Afterwards we need to add to the stack, so we have 3 arguments, 2 bytes each. And then we can do this endless loop right here, so we can debug it in the other debug it the other way. Hex to string end is not defined, that's true. So the end is here. SL not defined. That's weird. And annoying. Does that mean we cannot access the lower part of the SI? Because DL does exist. That's a weird thing. But I guess it works equally well with TX in this case. Alright, DL, this is referring to the EDX register, not the DI. Okay, glad I've caught that. DISI in this case. But then I get the whole 16-bit thing, and I was hoping I would only get the 8, but does it really matter? We shift it 5.4 and it like this. No, I think it will work equally well anyway. Well, let's try it out. What about this right here? This should also be DI, right? All of these should, because DI, let's see, DI is the buffer. Move DI SI. Maybe I changed too much here. So this should have been DL. Right, because we zero this out here and we want to copy that. So this could be DX SI instead. But why SI? Shouldn't it be DI? No, SI. So we take the cap. It should be, but number is more correct. But I think of it as character all the time. But okay, SI is the character. So we move into DX from SI. And then we shift SI. So the next time it will take another one. And we add DL. Let's add the whole thing. Then we compare DL. We add to DL. So DL contains our thing that we want to write. So we move into AL, DL, and we store that. Okay, now I think it's correct. Okay, it compiles at least. So what should happen now if it works? We should be able to go, let's see here. What are we using as a buffer? We're using this right here. Let's copy it into something just for the sake of it. into bx buff. So we know where to find it. So we check in bx, find the buffer, and we look the contents of that buffer. So we do info-reg, and we check ebx. So this is the address to our buffer. And then I guess we could just do xs on this address. Okay, it doesn't support s, but we can it support c? F49. Okay, so it works, but it takes it in the wrong order. Zero x 0F49 0F49. Yeah. And that kind of makes sense because of the way the memory works. But that also means we need to rethink one thing. So we need to start not at di, but at di plus 4. Or is it 3? So let's see. If we have a number A, B, C, D, we are currently pointing to, if we are writing to this one, 1, 2, 3. Then we write this 4 to 3, 3 to 2, 2 to 1. Four to 3, 3 to 2, 2 to 1, 1 to 0. And we compare, then we decrement. But maybe this should be 3, I'm not sure. Let's try that. and so we move into di this, and then we add to di 3. And instead of doing this, we need to do it manually. So we need to move a byte into DL. From AL, and then we decrement DL, and DL, DI. They should name these differently, right? We can use DL here instead, and we don't need this. Nor this. Nor this. Okay, let's try it now. Kind of cool that we have this debugger inside of Qemu, the virtual machine software. Makes stuff a lot easier. So let's see, UPX, this is the one. F. F49. Nice, this works pretty nice. So now we can at least convert into a string, a hex number. But this will be all for today. If you like this episode, please like and subscribe, and we will continue this project in a later episode. Thanks for watching. Thanks for today.